Okay, hi everyone. I'm going to be discussing lab exercise 3, higher order functions for list comprehension. Before we start implementing the functions that you're going to need to implement in this lab exercise, you need to understand how lists work in Haskell first. Haskell lists are written like lists in math. They look like these right here. So it looks like a math list like this one. 1, 2, 3, 4, like that. So lists in Haskell doesn't have to be lists of numbers. It could be lists of other things. So you can have lists of characters, for example, C followed by H followed by A followed by R, which will be converted automatically into a string when you try to print it. It could be a list of lists actually, and it's written like this: one, that's the list containing one, and then two, one, and then like that. So you have here a list of lists, and the elements are the list containing one, the list containing 2, 3, and then an empty list. That is how you write an empty list, by the way, like that. So one of the most important things about lists is that you can access the list as a whole, and you can access the elements inside the list. One thing you can do is you can concatenate the list using the plus plus function. So if you have one list right here, 1, 2, 3, 4, you can concatenate that with another list, 1, 2, 3, giving you a combined list 1, 2, 3, comma 4, comma 1, 2, 3. And this is what you use actually when you're trying to append or prepend into lists. So if you want to append a value to the list 1, 2, 3, 4, let's say I want to append 5, then I just use the concatenation. But you just make sure that what you're concatenating is the list containing 5, not the number 5, because that will give you an error. Because in Haskell, these two things are different. The first one right here on the left hand side of the equality is the number 5 itself, or the integer 5, while the expression that you see at the right hand side of the equality is the list containing the integer 5. If you notice, comparing these two will give you an error because you're not comparing two values of the same type. So again, to concatenate, make sure you're concatenating lists with lists. And if you want to prepend, you just have to transfer this one here, and it will be prepended, meaning it will be added to the start of the list. 5, 1, 2, 3, 4. You can find the length of the list using the length function. So the length of 1, 2, 3, 4 would be 4, of course. The length of a list containing no elements is an empty list, so it has 0 length. By the way, you can bind lists into identifiers as well. For example, I'm binding 1, 2, 3, 4 right here to L. So if I print L, I'm getting 1, 2, 3, 4. Just another thing to remember with Haskell. Haskell lists are not mutable. They cannot mutate. So meaning if ever you're trying to perform the following expression. So for example, you might imagine that this one will append a value to L. And it does, right? It appends 1 to 1, 2, 3, 4. If you try to print L again, you'll notice its value hasn't changed. It just so happens that the expression L plus plus list containing 1 will give you a new list, which is the list L appended with 1 as an element. But it doesn't change the value of L. L's value still remains that. If you want this specific longer list to be stored, then you store that to a different identifier. There you go. Great. Uh, so there are different ways you can access the elements of the list and the sublists in the list. There are four elements, four built-in list functions right here that you can use to sort of inspect the contents of the list. The first one of them would be the function called head. Let me clear some space a little bit. The head function, when you apply it to a list, it will return the first element of that list. It does not return a list containing the first element of the list. It contains the value itself. That is, it returns the value itself, not a list containing that value. So you notice that one right there that it returns, it is not surrounded by square brackets. On the other hand, the function tail L will return, accidentally wrote backslash, it returns all of the elements except the head. So since this is multiple elements, it's going to return a type which is list. So the tail of L is all of the elements 1, 2, 3, 4, except the head, which is 1, which gives you the list containing 2, 3, 4. So if you want to build L back again using head and tail, you can do this using concatenation. But remember that head L right here, head L is still a number. If you want head L to be concatenated correctly, you have to surround it with square brackets so that it becomes the list containing head L. So this one will rebuild head L and tail L together. So other than head and tail, you also have init right here. Init of L or any other list would return the list itself except the last element. And last would be the last element of the list, 4. Not the list containing 4, but 4 itself. So you need to familiarize yourselves with these functions right here because these are the functions that you use to traverse a list. Using these functions, you can traverse a list using the head-tail recipe. And this head-tail recipe right here will be the pattern of all of the functions that you're going to write in this exercise. So if, for example, if you want to create a function that adds 1 to the element of each of the to each of the elements of the array or list, you use the add 1 function that we created right here. So to demo what this add 1 function looks like, you provide it with a list of integers. You're gonna get 2, 3, 4, 5, 6, which is all of the elements of the original list, pero with added 1 in each element. Great. So let's dissect what this function actually looks like, what this function means, so that you can implement something that looks like this in the exercise. Because the functions in this exercise all look like this. Should have a bigger version of this written here. There you go. Let me erase that first. So you have this add 1 function right here. And if you notice, the type signature is list of int to list of int. And that is how you create the type annotation list of something. So if you want list of cars, then the type annotation would look like that. You just surround it with square brackets lang sad gihapon. So what is the definition of add 1? It accepts some L. And if you notice, this function right here is a recursive function. So you have to familiarize yourself with recursion in functional programming, since iteration is not really functional programming's thing. Its own version of iteration is just actually recursion, pero disguised as iteration lang. So what does this function mean? So you notice you start with the base case right here. And as you dissect this function right here, you'll notice how you notice that it does make sense. It does something very intuitively. So the base case is very intuitive. If the length of L is 0, meaning if L is an empty list, then you just give back the empty list itself. That makes sense, right? If you add 1 to all of the elements, which are none, there are no elements, then you give back no elements lang yapon. So that one makes sense. That is the base case of this recursive function. Otherwise, if the length is not 0, what you're going to do is this specific recipe right here. So this specific recipe works in the following way. Start with a head, then deal with the rest, or the tail. Deal with the tail. Start with the head, then deal with the tail. So what is it doing? It starts with the head. Since what you want to do in this function right here is to add to add one to all of the elements of the list. So it starts with the head. It adds one to the head. That's what it does first. Then it deals with the rest. How does it deal with the rest? It calls the function add one tail L. Because if you recall, what does the add one function, what is the add one function supposed to do? It is supposed to add one to all of the elements of the list. And since you have already done adding one to head right here, then you're gonna worry about tail L na lang. So if you're gonna trace how this function works, let's say you're calling add one to the list containing 1, 2, and 3, for example. If we trace this, so it's going to start with checking if the length of the list is L. If length of L is equal to 0, then return an empty list. It is not less than 0, or is not equal to 0. So it goes to this part right here. It goes to the average case, or the not base case. So what is that? What it does there is it starts with the head. So the head is 1, and it adds 1 to the head. So that will become 2. And then enclose that in square brackets to convert that into the list containing 2, and then concatenates that with the call to, oops, no brackets, the call to add 1 tail L. So what is the tail of L? Let me just write it down right here. I think I need some more space later, so let me rewrite that. So again, since we go inside here, we're going to start with the head. 1 plus 1, that becomes 2. And then we concatenate that, the list containing 2, with add 1 tail L. Add 1. What is the tail of L? The tail of L is 2, 3. There you go. So how is this expression evaluated? That is another recursive call to add 1, 2, 3. So this recursive call will be evaluated inside the else clause right here, because 2, 3 is still not length 0. So it doesn't go through the base case gapon. So add 1, 2, 3 will evaluate into, first, starting with the head, 2. Add 1 to 2, or plus 1 right here. Plus 1 to the head gives you 3. Enclose that with square brackets to convert it into a list, and concatenate that with add 1 tail L. What is the tail of 2, 3? The list containing 3. And then what does this function call evaluate into? So since the length is still not equal to 0, we're still not going to go into the base case. We're still going to go through this case right here. So starting with the head, what is the head of 3? The head of the list containing 3, the head of the list containing 3 is 3 itself. Add 1 to 3 here. So 3 plus 1, it will become 4. Enclose that into square brackets to convert it into a list containing 4, and concatenate that with add 1. What is the tail of 3? So the tail of 3 is actually just the empty list, because it actually doesn't have any elements besides the head. So it's just going to add 1 to an empty list. So in this case right here, what does this evaluate into? So since the length of an empty list is 0, so we're going to go through the base case. The base case returns an empty list. So evaluating all of this right here, it will be 2 concatenated with 3, concatenated with 4, concatenated with an empty list, giving you 2, 3, 4, which is the result that you're going to expect when you're calling add 1. That makes sense? That does make sense. So since we're done dissecting this one right here, let's move on to the functions that you need to implement for this exercise. So I've written down the dissection of that function one by one right here in this instructions. So which functions are you gonna implement? The functions are called mymap, myfilter, myfoldl, myfoldr, and myzip. So these are your own versions of the built-in map, filter, fold functions in Haskell. So that's the reason why the names for these functions have the prefix my underscore to uh, avoid causing errors for Haskell, since the map, filter, fold, L, fold, R functions are already reserved for its own versions of those. So you're not just gonna call these functions inside your mymap function, for example. You have to implement them yourselves. So starting with mymap, the map function accepts a function f and a list with elements of type A. It returns the list with elements of type B. So you'll notice here, this is new syntax that I'm introducing. You'll notice the type annotations of these start are of lowercase letters. These are not actual types. These are type variables. They represent types. So since I've written A right there, it will accept the first parameter that it accepts is a function, which is an A to B. An A to B would be any to any type. So it could be an int to int. It could be an int to char function. It could be a char to int function. Okay? Uh, to generalize that it accepts any to any function, we're using the type variables A and B. It doesn't have to be A and B. It could be any other lowercase identifier. But it also accepts another type A. So meaning, if what you're giving mymap is an int-to-int function, then the other parameter it accepts should be a list of type int lang sa gyapon. If you're giving it int to char, then list of int lang sa gyapon. If you're giving it a char to int function, then you should give it a list of char. Okay? And then finally, this mymap function will produce type B. So for an int to int, it should produce an int, a list of ints, sorry. For an int to char function, it should produce a list of chars. Here, a char to int function should produce a list of ints. So that is how you interpret these variable type annotations. Okay. So what does the map function do? Let's actually demo this using Haskell's own version of map function. So map, for example, we're giving it a function. Let's say the function we're giving it is the successor function. Let's say I'm gonna create the successor function using an anonymous function right here. And then we're gonna give it 1, 2, 3, 4, for example. So this mapping right here should return 2, 3, 4, 5, which is all of the elements of map, or sorry, all of the elements of 1, 2, 3, 4. All the elements are applied to the lambda that you provided as well. So you can actually read this here in the description of this function. If you're giving it a list containing L sub 1, L sub 2, L sub 3, and so on until L sub n, for example, that list, then if you map the function f to this list, then the result you're getting is a list containing f of L1, comma f of L2, comma f of L3, and so on until f of Ln, or the last element. So all of the elements are applied to the function f that you're also giving it. So for example, if we use another example, let's say we're using the double function. Not sure if I've implemented the double function. Let's check. So the double function just doubles an integer. So if we map the double to the list containing 1, 2, 3, 4, it should double all of the elements of that list. 2, 4, 6, 8. We can do interesting things right here because the types that map accepts are generalized into A and B, right? So for example, if I give it the head function, if you remember, the head function accepts a list, right? So meaning the list that you are providing to head function should be a list of lists as well. So for example, this is the list of lists. I am providing map of head. There you go. So if I run this right here, I'm going to get the heads of all of those lists. So 1, 2, and 1. And the types right here work because the return type or the type map head produces should be a list of integers because head accepts lists and returns integers. If I replace head right here with tail, what it's going to produce is a list of lists because tail returns a list as well. If I try length on the other hand, I should get back a list of the lengths of the lists that you provided as parameters. So the length of 132 is 3, the length of 22 is 2, the length of 1 is 1. Great, amazing, makes sense. So that is the map function. You just have to implement that using this my map function right here. So to test if the function you created is correct, just use the Haskell's built-in map function. You don't have to import anything. It's already available. The next one is the filter function, myFilter, which does this. If you provide myFilter, so myFilter or Haskell's filter accepts a function of type a to bool, meaning it accepts some predicate, a function that produces some Boolean value, true or false. So for example, this one is an example of a Boolean lambda. This one just checks if the value that I'm giving it, is it greater than 0 or is it a positive number? So if I apply it to this list right here, containing 1, 2, 3, 4. Oops, those are all positive numbers. Let's mix in some negative numbers as well. There you go. So based on its name, filter should filter out all of the elements of the list which does not satisfy the predicate that you're giving it. So the predicate that we're giving it is just this positivity check. So all of the non-positive values will be discarded. It will be filtered out. You're going to be left with 1, 2, and 2, which the order of which is retained right here. Let's say we use this list right here, and let's say what we're going to call is filter it with all of the lists that are longer than 2. So it should be length of y should be greater than 2. So just to dissect what I'm actually doing right here. So the predicate that I'm giving this filter function right here is the length of y must be greater than 2, meaning I'm filtering out all of the lists that are less than or equal to ang ilahang length. So I'm going to be filtering out everything except 1, 3, 2. If I increase the threshold right here to 3, I'm going to get an empty list because all of the elements of the original list were filtered out. So that is filter. So the challenging functions that you need to implement in this exercise would be the fold functions. And there are two versions of the fold functions that are very similar to each other. You have fold L and fold R. They stand for fold left and fold R. So this is how they work. So fold R accepts three things. It accepts a function, which is an A to A to A. So this is a function that accepts two A's and returns another A. So meaning it could be a function that accepts two ints and then it returns another int. It could be a function that accepts two characters and it returns another character. It could be a function that accepts two booleans and returns another boolean. So meaning they are all A types. That's one of the things that it accepts, the function. I'm going to call this f. Another thing it accepts is the seed value. Oops. And the type of the seed value right here is also type A. This is the seed value. And I think the variable I'm using for the description is U, I think. That's right, U. And then finally, I have the list of A's. And it will return just a scalar value or a single element of type A. A single value of type A. This is the return. This one is the list, L. Okay. So how do the fold functions work? So starting with fold L, which stands for fold left, if you're starting with a subtraction function, let's say you have the function you're using right here is subtract. I'm just gonna use the word subtract right here so that I do not write a lambda function again and again. So let's say subtract's definition is that it accepts a. Let's not use a again. It accepts x and y and it returns x minus y. Very simple. It subtracts y from x. Cool. So if you use this for your fold L, it is compatible because the subtract function is int to int to int. It accepts two ints and returns another int. So check ang iyang type. The seed that you're giving it should also be of type int, and the list that you're giving it should be of type list of ints. So for example, I'm calling fold L with the subtract function. I'm giving it the seed value 3, for example. I'm giving it the list 1, 2, 3, for example. And what does it return? So this is how you manually calculate the value of a fold left. So the clue right here is actually found here, or right there. So starting with the value 3, or the seed value 3, you subtract that with the first element, which is 1. After that, whatever is the result of this subtraction, you subtract that with the second element. Whatever is the result of that subtraction upod, you subtract it with the third element. And since there are no elements left, that would be all of them na lang. So what would be the result if you're calling fold L for this specific parameters? So that would be 3 minus 1, which is 2, minus 2, which is 0, minus 3, which is negative 3. Okay? So if I use those parameters, I should get the same answer. So fold L of the function, let me define the subtract function first. Should be equal to x minus y. So fold L of subtract, I'm giving it the seed value 3, right? And then I'm giving it the list containing 1, 2, and 3. If we're correct, we should get negative 3, which is we're correct. We got negative 3. What about fold R? How is it different from fold L? So fold L does that. Fold R does this. If we use fold R, subtract 3, and the list 1, 2, 3 lang sa gyapon. So what's gonna happen? So starting with L1, or the first element of the list 1, let me give a little space right here. Starting with 1, what you're gonna do is you subtract, you start with 1 and then you subtract that with the result of the second element minus the result of the third element, minus, since the third element is the last element, we're just going to be subtracting this with the seed value, which in this case is also 3. That is fold R. So the result for this one will be 1 minus 2 minus 3 minus 3. So 3 minus 3 is just 0. So 2 minus 0 is just 2. So you're going to be ending up with 1 minus 2, which is equal to 1. So if we got the correct understanding for fold R, this should give us negative 1, which is what we got right here. 1 minus 2 is negative 1, not 1. Negative 1. There you go. Another important thing to notice right here is that fold L and fold R will have the same answers if the function that you're applying it to is a commutative function. For example, addition is a commutative function, right? So if I replace this subtract function right here with an addition lambda, x, y to x plus y. So since addition is commutative, fold L will give us 9, and fold R will give us the same answer, 9 as well. Okay? So make sure you don't interchange the definitions for fold L and fold R. Okay? To make sure you got the right answer, just compare that with Haskell's own definition of fold L and fold R. Moving on, we have the myZip function. The zip function accepts a function f and two lists L. So let's say the first list is called L and then the second list is called M, and it returns a new list K, which is of this value right here. F of L1, M2 ang first element. The second element is F of L2, M2, and so on. So for example, you have two lists. You have 1, 2, 3, 4. That's the first list. I'm going to call that L. The second list, M, would be, let's say, 5, 6, 7, 8. Let's say the function that you are adding, or the function that you are providing here, is the addition function. So lambda x space y to x plus y. So the result of zip, this function, lambda x space y to x plus y, given these two lists right here, I'm not going to write them down. Let's say I'm just going to write down L and R, L and M na lang. The result of this usage of zip would be, first, the first element of the resulting list would be 1 plus 5. So that is the first element plus 5, plus because that is the function that we're using. The second element is 2 plus 6. The third element is 3 plus 7. The fourth element is 4 plus 8. And that's the result of the zip function. The reason why it's called zip is because if you imagine this list right here and then another list, if you use a zipper, for example, I don't know how to draw a zipper. You pull down the zipper and it will, let's say, close these two lists into one whole list, for example. Does that make sense? In my head, it does make sense. Maybe I'm just rambling. Anyway, the best way to explain this one is to demo the zip function. Actually, I'm not sure if the zip function exists. The zip function does exist. Or, yeah, okay, so the zip function accepts an A to B to C. So I'm gonna give it an int to int to int, that's allowed. So an addition function should look like this: x plus y producing, x and y producing x plus y. That's an anonymous function. I'm gonna give it two lists. The first list is 1, 2, 3, 4. The second list is 5, 6, 7, 8. Oops. I think uh, Haskell's definition of zip is a bit different. Anyway, if you're, yeah, it is a bit different, but the just follow the definition that I'm using for the exercise right here. Just follow the instructions that are written in this markdown file, the instructions. Don't follow Haskell's own definition of zip. Follow mine. Okay, it's a bit of a unexpected. I forgot how Haskell zip works. Anyway, the last function that you're gonna implement is, without using loops, using the functions that you have created above instead, write the following functions. First, given a list of numbers, return the sum of the squares of the numbers. The second one, given three lists, a list of first names, a list of middle names, B, and a list of surnames, C, return a list of whole name strings or list of cars. That's what strings are in Haskell. I've demoed that kanina, right? Where the length of the string is an even number. So the example right here, whole name, that is what the function should be called. So given those three lists, the behavior of this function should be that it combines that string into one name. So what you are going to do for these two right here, for this function and then this function right here, what you're going to do is that you're going to use a combination of map, filter, fold, and zip. Just by using those, you have to implement these ones right here. If you notice right here, this name should appear, but one of the instructions is that the length of the string, including spaces and periods, should be even. So foo s, s.abcd right here, that name is filtered out because it doesn't satisfy one of the instructions, which is this. Okay?